Welcome to Radio Systems Design, Module 7, Two-Stage Conversion Transmitters. In this module, we're going to cover two-stage upconversion architecture and talk about some of the advantages and disadvantages. And then in particular, we're going to talk about the intermediate frequency, or the IF, and what are some of the constraints and motivations for choosing a specific IF and some of the trade-offs. So the motivation for two-stage upconversion is that several of the signal impairments that we saw in direct conversion can be reduced or eliminated if we use a two-step conversion or a heterodyne transmitter architecture. Direct conversion is often called homodyne, and heterodyne transmission means that we're going to take a two-step or two stages of conversion before we get to the final transmitter. So in a two-step converter, we intentionally don't choose the initial LO to be at the final carrier, but rather choose a different frequency, omega 1. And then what we do is we then take this signal and we upconvert it by a second LO at omega 2. And if you remember what happens if we take an AM signal and modulate it from the previous modules, you can see that our baseband signal, which may have started out like this, then moves up to where this is omega 1, and now this entire spectrum is going to be upconverted right around omega 2, and we're left with our upper sideband and our lower sideband. And this should be familiar to you from the analog modulation module. Now typically what we're going to do then is just filter out 1/2, because remember we don't need both sidebands. We can do this through a simple filter, or we saw in the past that we could use a few more advanced architectures such as a Hartley transmitter. The reason why that may be not desirable in a two-stage conversion is that you'd have to do it for both phases, so you'd have to repeat the transmitter twice, and that may be undesirable. So for simplicity, if we can find a filter that works, that actually works pretty well for us. And once again, we would need some sort of PA at the output to increase the power for the transmission. And as you've seen all along, we call omega 1 the intermediate frequency, or IF. And so it's always going to be referred to as IF. And it's basically the omega 1 will be the difference or the offset of the signal from our final RF carrier. And I should just mention too here that omega 2 is what we would call the RF signal, if you will, or the RF carrier. And so omega 1 is really going to set this offset. And so you can already think I can make omega 1 very high, and that's going to move this far over, right? Or I can make it very small, and this distance here would get closer. And so there's some trade-offs between both of those that we'll see in a moment. So one of the benefits of this architecture, as you can see here on the bottom of the slide, is that neither of the LOs appears in the signal, right? So any carrier leakage is just going to pop up at the original omega 1 and omega 2, but doesn't show up at our signal. So that's the major benefit, is we've eliminated any carrier feed through that might be a problem for us. And another nice thing is that the omega 1 is operating at a much smaller or lower frequency than it would in a direct conversion. And this allows us to have better phase noise. It allows us to have better matching for phase and amplitude. Just because it's at a lower frequency, it's easier. We have more control over the items. And then the LO here, we still have phase noise problems like we did before, but there isn't any more amplitude phase mismatch issues, because all of that's taking care of the signal that's coming in. It's just upconverting that single signal. Another thing is that we talked in the past that the gain and level control was hard to do at higher frequencies, but with a two-stage conversion, we basically can do all of that here at this intermediate frequency. So what you're seeing is that with the two-stage conversion, not only are we getting rid of the feed-through problems, we're also able to do all of this low-frequency circuitry in a much easier way. So basically, this up conversion to Omega 1 and the amplification at Omega 1 is at much lower frequencies, so it's easier to implement in either discrete or in integrated circuits. So there are some disadvantages to this architecture. And the obvious one to start out with is you need two local oscillators. You also need an additional mixer, as you can see here. And as I talked about before, the filter is critical here because you need to filter out pretty well, or if you will, I want to keep this and I want to get rid of its image that would be, actually the lower sideband is what it would be called. The image is what we call on the other side and the negative frequency domain. So we want to be able to get rid of the lower sideband. And you need a pretty good filter to do that. A lot of cell phones now use surface acoustic wave filters, SAW. And what they are is they basically take an electrical signal and they launch it on a piezoelectric substrate in a way that it only transmits a very narrow band of frequencies. And the reason we do this is these filters are extremely low insertion loss and extremely sharp filtering, and so it's worth it to go into a specific technology just for these specialized filters. So let's talk a little bit now about the choice of the intermediate frequency. And as I said before, the distance between Omega 2 and where the signal is going to be Omega 1. And so basically this intermediate frequency is going to choose where we are with respect to Omega 2. And so the question is, how do you choose Omega 1 and Omega 2? By the way, they both need to sum up so that this is your target center frequency, right? And so what does that mean? That means if I want to be operating at, let's say, 920 megahertz, right? And Omega naught is 20 megahertz, right? Then Omega 2 could be 900 megahertz. Omega 2 would not be 920 megahertz, right? Because we want to center it right there. And so if we make the IF low, we have some benefit of these components are easier to make. There's less mismatch between the phases, between the I and the Q. And so basically it's just easier to implement. So a low Omega 1 would really help us in making this low frequency section in an actual radio. The challenge and the problem is that as we decrease Omega, the challenge with this is that as we make the LO or Omega 1 small, we move this signal closer and closer to Omega 2. And so we run the problem of this actually getting, if you will, if you move it too close, it may overlap with the carrier and we would have the leak-through problems we had before. And the other problem is that, remember, I need to get this filter to keep this one sideband I want. The closer it gets to Omega 2, the closer the lower sideband also gets to Omega 2, and the sharper the filter I need. So Omega 1 ideally should be much larger, as large as I could make it, to benefit both the LO leakage and the bandpass filter. So the choice of the IF is not trivial. It really is a system trade-off between your low-frequency circuitry and your high-frequency filters and need for rejection of LO. So typically, there's a wide range that you could choose your IF to be in any system, and you're going to make an engineering trade-off between the specific circuitry and implementation of your baseband, the quality of your filter, and your final signal desired. All right, so this completes this module. We discussed two-stage upconversion architectures, also called heterodyne upconversion. We talked about the advantages, which was it eliminated the problem of the LO leakage, and it also allowed us to build the I and Q stage at a much lower frequency, which made it better for mismatch and balance and phase noise. And the disadvantages were it's more complex, and also we need a really good bandpass filter. And then we talked about the choice of the intermediate frequencies, and mainly the trade-offs there are between LO leakage and the filter, and making the low frequency circuitry operate in a convenient low frequency. So if we choose Omega 1 to be very low, that makes the I and the Q stage easy to do, but we need a much better bandpass filter at the output. We run the risk of LO leakage. Whereas in the contrary, if we make Omega 1 very high, it's easy to filter out. We don't have to worry about LO leakage, but then our I and Q stages are operating at a much higher frequency, and that makes them a little bit more challenging.